So as we continue with factoring, the next thing we want to look at with factoring is what's called special products. So these kind of create some nice patterns that if we can just recognize the pattern, we can factor this rather easily. So the first one we're going to talk about is recognizing the factor, how to factor the differences of two perfect squares. Remember, square means this power of two concept. So before we can factor such a special product, we must be able to recognize an expression as a special product. First, we have to examine a sum and difference of the same two terms, of same two terms. The product is what's called the difference of two squares. So first off, as far as squares go, squares are things that are raised to a power of two. So like 1 squared is 1. So 1 is called a perfect square. 2 squared is 4. So 4 is called a perfect square. 3 squared equals 9. So 9 is called a perfect square. Write a few more. Eight squared is 64. 9 squared is 81. 10 squared is 100. So these are some numbers that if you're familiar with, this makes things a little bit easier. So the 1, the 4, the 9, the 16, the 25, the 36, the 49, the 64, the 81, the 100, those are all examples of what we call perfect squares. So to recognize a difference in squares, the first thing is we have to verify that each expression is a binomial. In other words, there's two terms. So if it's two terms, that's the first thing we're looking for. The next thing is we want to verify that each term is a perfect square. If each term is a perfect square, then we got that going on. And then the second term has to have a subtraction sign in front of it. In other words, it's got to be a negative in front. So what we're looking for is a squared minus b squared. If it meets this form right here, it's called a difference of squares. So if we look at these examples here, would they represent a difference of two perfect squares? Well, there are two terms, and there is a subtraction sign. There is a subtraction sign between them. In other words, the second term is negative. The other thing is, are they each a perfect square? So notice how on A, x is a perfect square because x squared, it has a power of 2. So that power of 2 is kind of a giveaway. That 9 can be written as a power of 2 as well. It can be written as 3 squared. So it does check. A would be a difference of squares. It would meet that. If you look at B, notice how the first term is a perfect square because it's raised to a power of 2. And we know that 7 squared is 49. So that's a power of 2 as well. But notice how the middle sign is not a subtraction symbol. So it's not a difference of squares. So if I look at C, we have m squared minus then this 27. But notice how 27 is not a perfect square. There's nothing I can actually square, not a whole number, if you will, that would actually give me this 27. Because we know that 5 squared is 25 and 6 squared is 36. So 27 is not a perfect square. So B wouldn't be, that's a no. C would be a no as well. If I look at D, the 3y squared is not a perfect square because that 3 is not. That's actually would have to be like a 9 or something. So D is not because that first term crashes. If I look at E, notice that 3x squared does give me 9x squared, and 2 squared does give me 4. And notice how there is a minus sign between them. So E would be an example of a difference of squares. F, right off the bat, it has 3 terms, so it's not even a binomial, so that crashes. So what we're looking for are things like A and E. Those are what we call difference of squares. So what we want to do now is once we recognize the difference of squares, we want to know how to factor difference of squares. Remember, factored form involves rewriting it as a product of two. In this case, it's going to be a product of two binomials. So what we do is we take the square of the first term and we take the square root of the absolute value of the second term. In other words, ignore the negative, if you will. So if that holds true, then we're good. And then what we do is we write one factor as a sum of square roots, and we write the other one as a difference of square roots. What that means is one of them has to be we have to have a plus between the two terms, and one has to have a minus between two terms. So sometimes they overcomplicate us with some of their vocabulary. They're just trying to be perfectly accurate, but some accurate vocabulary kind of confuses us. So if we can write something in the form of a squared minus b squared, then it's going to be this binomial times this binomial. And that's how we have this, what we call that conjugate pair, a plus b times this a minus b concept. So we have the same two terms, but one of them is going to be with a plus sign between them, and that one's going to have a minus sign between them. So if I want to factor x squared minus 9, notice how I can write the first term as a power of 2. I can write the last term as a power of 3. 3 to the power of 2, I should say. Notice how that's a difference of squares. So notice how we then use this a minus this 3 times this a plus this 3. Or again, you could have wrote it as a plus 3 times a minus 3. Remember, in multiplication, order does not matter. As long as one of the factors is a plus 3 and one of the factors is a minus 3, it doesn't matter what order those are in. So that's kind of how we approach this. So mentally, if you can see that this is a perfect square, you know, x squared is a perfect square, and what squared gives you 36, if you can see that as a 6, that means this is a difference of squares. So what we have then is essentially this x and this 6 as our two pieces. So we have this x minus 6 times the quantity, then this x plus 6. That would be the factorization of that difference of squares. It's going to be that conjugate concept. One of them's going to be minus and one of them's going to be plus, but it doesn't matter which one's minus, which one's plus. This one here, the C one doesn't look as easy because of that 4x squared there. But notice how 4 is a perfect square, that would be a 2, and x is a perfect square. Alrighty, so notice how I can write that as 2x squared. That's the same thing as 4x squared. And as we mentioned, 1 is a perfect square because that's 1 to the power of 2. It's still going to be 1. So 4x squared minus 1 can be rewritten as a difference of squares. So that means we can factor it as then 2x minus 1 times the factorization of 2x plus 1. So it does factor into that form, 2x minus 1 times the quantity 2x plus 1. Now D looks a little weird. What we can do, though, to make it look a bit easier is just rewrite the terms in the other direction. 16m squared minus this 49. So if I put the terms in the other order, this now looks a little bit more familiar to us. So remember, terms can be rearranged as we see fit. And remember, with a polynomial, we usually like the highest degree to go first anyway. So those were kind of backwards to begin with. So we need to rearrange it from highest degree to lowest degree. So if you think about that, you know, what can you take the square root of, or what's the square root of 16? You know, again, or what squared is 16, we should say. Same kind of thinking. We should have like a 4m there. Again, you can take the square root of 49, or what squared gives you 49 is a 7. So remember, you can use your calculator and use the square root symbol, or you can just mentally think this out. 7 squared does give you 49. So notice how this is a difference of squares, actually. It is factorable. So this is going to factor into then 4m minus 7 times the quantity 4m plus 7. And again, if you write it as 4m plus 7 times 4m minus 7, that's still correct. As long as one of them is plus and one of them is minus, that's what we call factored form. So next thing what we want to get into is what's called how to factor a perfect square trinomial. So again, a trinomial means we have 3 terms. And what does a perfect square trinomial look like? Well, what we pick up on is the first and last terms are going to be perfect squares. And then the middle term is going to be twice the product of those square roots of the first and last terms. So we need to be able to recognize these special products so we can actually apply the strategy. So to identify that a trinomial is a perfect square trinomial, the first focus is on the first and last terms. They have to be perfect squares. So let's look at this example here. x squared plus 14x plus 49. If I want to try to identify that this is a perfect square trinomial, our attention's on the first term. So notice how x squared is the same thing as, that is a perfect square. And 49, notice how that is the same thing as 7 squared. So the first term and the last term are perfect squares. Now the catch is, when you multiply the 7 times x and double it, in other words, if you multiply by 2, so 2 times 7x, if that gives you the middle term, then this is going to actually be a perfect square trinomial. So it does, so therefore this is a yes. That's what we're looking for. The first term's got to be a perfect square. So notice how the x is raised to the power 2, so it's a dead giveaway. The 49 is not as obvious, but 7 squared does give me 49, so it passes those two tests. And then the key is when you multiply the x times the 7 and double it, if it gives you the middle term, then it does become what we call a perfect square trinomial. So if we look at 4m squared minus 12m plus 9, is this a perfect square trinomial? Well, 2m squared does give me 4m squared. 3 squared does give me my 9. So if I multiply these two together, that's going to be 2m times 3, which is going to be 6m. If I multiply that by 2, does that give me my middle term? Yeah, well, all we got to do is make sure that we have, say, notice how this actually would have been a negative 3 squared would have gave me this 9. So I could actually call that, that negative. So what we pick up on is, if the sign in the middle is negative, then that last term actually had to be a negative in that sense. So it does pass all 3 tests, because we do get a negative 12m. Because remember, you could be squaring a positive number or a negative number to get that 9. So technically, to get that middle sign of a negative, that last term was actually a minus. So in other words, we need a negative in that second term, that last term position. So that is also an example of a perfect square trinomial. So again, if I want to verify that this is a perfect square trinomial, we have this 3x squared does give me 9x squared. 4y squared does give me 16y squared. Now, if you multiply these two together, that's going to be 12xy. And if I multiply that by 2, if that gives me the middle term, then it's a perfect square trinomial. And 2 times 12xy does give me 24xy. So therefore, this is a perfect square trinomial. It does check out. So that's kind of what we're going to be doing to factor in them. So notice how we basically have this format a squared plus 2ab plus b squared. If I can make the trinomial meet that format, notice how it's going to be a plus b squared. If I have a squared minus 2ab plus b squared, notice how if that middle sign is negative, then we use a subtraction sign between our two terms to make it a perfect square trinomial. So we want to factor the following trinomials. So to be perfect square trinomials is the first term of perfect square. Yeah. Is a 49 a perfect square? Yeah. Now the catch is multiply the 7 to the x and then double it. In other words, multiply by 2. Does 2 times 7x give you the middle term of 14x? Yeah. So what this turns into then is this x becomes my first piece and the 7 becomes my second piece. So this becomes then x plus 7 to the power of 2, x plus 7 squared. So remember, if we want to expand that out and check it, remember how we could write this as a binomial times a binomial. And if we use FOIL, we would have x squared plus 7x plus 49. And that's how, if I expanded it back out, it would give me x squared plus 14x plus 49. So it does check out. So, but when we write it in this x plus 7 in parentheses squared, that's considered the factored form. So 4m squared minus 12m plus 9, well, 2m squared does give me 4m. 3 squared does give me 9. If I multiply these two together, 2 times 3m is 6m. But again, if I multiply that by 2, does that give me my 12m? Yeah. And since we pick up on that this middle term was negative, this actually was a negative over here. So in other words, we should have a subtraction symbol between the two. So 2m minus this 3 squared becomes our factored form. So 9x squared plus 24xy plus 16y squared. Again, notice how the 3x squared does give me my 9x squared. 4y squared does give me my 16y squared. Then if you multiply the 4y times, the 3x and the 4y together, that gives you 12xy. But then if you multiply it by 2, it has to give you the middle term. Well, that does give me 24xy. So it does pass all the tests. Therefore, it does factor as then 3x plus this 4y squared. All righty. So those are the two ones that we will look at as far as special products go.